today, the discussion we had started in the last lecture. So let us begin. So this is session number 6 for us, and we will continue ahead with kinetic theory of gases, which we had started in the last lecture. Okay, so quick recap of the things that we've learned so far. We saw the assumptions of the kinetic model. Okay, in that the most important things were the fact that the collisions are perfectly elastic, and the fact that there is Brownian motion for gas molecules. So Brownian motion means that we saw that this became equal to 3 times Vx average square, or 3 times Vy's average square, or 3 times Vz's squares average. Okay, so this was the Brownian motion concept. Then we saw that we looked at the relation of RMS velocity with respect to pressure and volume. So this is the main important derivation that we have done so far. So we saw that Vrms, or the root mean square speed, comes out to be square root of 3 PV divided by total number of molecules into mass of each molecule, or we can also equate that with total number of moles into mass of each mole, or molar mass. So these are the important aspects of kinetic theory of gases that we have discussed in the last lecture. Of course, there is a longer list of assumptions, but I'm telling you these are the important assumptions as far as the derivation is concerned. Okay. Next thing we will look at today is the kinetic interpretation of temperature. So this is very important. So the kinetic theory type of interpretation of temperature is that the absolute temperature of an ideal gas, capital T, which is measured in kelvins, it is a quantity that is directly proportional to the average kinetic energy of the gas molecules. Okay. So that is the interpretation of temperature according to the kinetic model, that the absolute temperature of a gas, which is the temperature measured in kelvins, that is a quantity which is directly proportionate to the average kinetic energy of its molecules. Okay, so we put this into an equation. That means that this quantity, okay, because we can write the average kinetic energy of a gas molecule equals to this, and that is directly proportional to temperature. So if we now connect it with this equation above, we can see that because 3 and 2 are just numerical numbers, they are dimensionless quantities. It's directly proportional to the average kinetic energy of its molecules. average kinetic energy of its molecules. Is it clear now? So the constant of proportionality here is called the Boltzmann constant. So this is number of molecules. So basically it is equal to number of moles into Avogadro's number. Okay, so next up, where R, which is basically equal to Avogadro's number into Boltzmann's constant. This is called the universal gas constant. Which means that it's universally constant for all gases, regardless of the other properties of the gas. Okay. That R, which is equal to the product of pressure into volume divided by number of moles into temperature, will be a constant for any gas at any pressure, volume, and temperature, where n is the number of moles. So experimentally, the value of R is determined to be 8.314 joules per mole Kelvin, because the product of pressure into volume has dimensions of force per unit area into volume. This, so that's why pressure into volume, the SI unit for it becomes joules. So pressure is expressed usually in pascals in SI unit, where 1 pascal is equal to 1 Newton per meter square, and volume is expressed in meter cube. So 1 pascal into 1 meter cube is equal to 1 joule. So this value that we have of the universal gas constant, this is determined from experiment. There's no theoretical way to verify this. So till date, the information that you have about this equation, which is called the ideal gas equation, used to come from the combination of Boyle's law and Charles' law, which are the two experimental laws again. Boyle's law being that if you keep a gas at constant temperature, then its pressure is inversely proportional to its volume. And Charles' law being that a gas kept at constant volume, its pressure is directly proportional to its temperature. So combining the two laws used to give us this ideal gas equation. But here you can see that it's not coming from some combination of Boyle's and Charles law and experiment determination. It is coming directly from the assumptions of the kinetical model, the kinetic theory of gases, the assumptions that it applies to gas molecules and their behavior, that there is no interaction other than collisions, all the collisions are perfectly elastic, the gas molecules follow the perfectly random motion and Brownian statistics, etc. So with those assumptions in mind, the derivation that has been done, that has given us a theoretical way to derive that product of pressure into volume should be proportional to the product of number of moles into temperature, or number of molecules into temperature, whatever be the case. And the in between thing is R, which is the constant of proportionality, which becomes a universal constant for all gases. So there's an important set of derivations here. So I will just leave you with a minute to go through it. Yeah, value of Boltzmann constant is very simple. It is universal gas constant divided by Avogadro's number. We'll write that in the end, don't worry. So Boltzmann constant is given by this relation, that it is nothing but the universal gas constant divided by Avogadro's number. Yeah, that's correct. So the thing is, in calculations, we hardly ever use Boltzmann constant. What we use is the universal gas constant, capital R. So you remember the value of capital R, the universal gas constant, 8.314 joules per mole Kelvin. So this is called the ideal gas equation because it is the equation of state for an ideal gas, one that yes. Okay. So pressure, volume, and temperature, these three things, they refer to the state of a gas. So the relationship between pressure, volume, and temperature is called the equation of state. So for example, suppose we have a question like this, that hydrogen gas is in a heat sealed container, okay, at a pressure of 2 atmospheres, volume of 5 liters, okay, and number of moles is equal to 3 moles. Okay. So first of all, find the temperature. Take the value of R as for this. Determine the total kinetic energy of gas molecules in the container. Okay. We will just make a small adjustment. We will change the gas from hydrogen to helium. I'll explain to you later why we are changing it from hydrogen to helium. We can do the question as per hydrogen also, but here, to make the second part technically accurate, we will change it from hydrogen to helium. Okay, so just try this out. Okay, so let's determine the first part. So pressure is equal to 2 atmospheres, which will approximate as 2 into 10 raised power 5 pascals, because 1 atmosphere is 1.01 into 10 raised power 5 pascals. So approximately 10 raised power 5 pascals. The volume is 5 liters. So that is 5 into 10 raised power minus 3 meter cube, because 1 liter is 1000 milliliter, which is 1000 cubic centimeter. So that is 1000 into 10 raised power minus 6 meter cube. Okay. So these are two standard these things conversions that you should know. And number of moles is equal to 3. So temperature will become PV upon NR. So 2 into 10 raised power 5 into 5 into 10 raised power minus 3 divided by number of moles into 8.314. So this should give us the temperature in kelvins. Okay. So that's 10 raised power 3 divided by 3 into 8.314. Okay. So that will give us 1000 divided by this, which is about 40.1 Kelvin approximately, which is albeit an extremely low temperature for a gas. Okay, now let's come to the next part, the total kinetic energy of the helium gas molecules. How we'll calculate that? So for the total kinetic energy, should be equal to half of total mass. Okay, this is the total average kinetic energy. Okay, so that is okay. So this will become our answer. Yeah, we can use that also, Aditya. It will come out to be the same value. You can use that also, that per molecule, the average kinetic energy is 3 by 2 kT. Multiply that with the number of molecules, which will be number of moles into Avogadro's number. So this thing that we've written, this can also be equated. That can also be equated as, okay. But it's just easier to calculate this way with the data given over here. Okay. So anyway, I hope this is clear. Now let's look at another question. So we have a closed glass tube with this is a mercury pellet. Okay. Now initially the glass tube is sealed. Okay, so initially the tube is in the horizontal position with the mercury pellet at a centered position, and hydrogen gas on either side at 2.5 atmospheric pressure as shown. So what is happening when this is at the midpoint initially is that this and this are each 200 centimeters, and the total length of the tube, let's say 450 centimeters. So there is hydrogen gas at 2.5 atmospheric pressure. Okay. And the surrounding temperature is 300 Kelvin. Okay. Now next what we do is, now the tube is taken to a vertical position. Okay. So from this horizontal position, change the position of the tube to this vertical position. So the mercury blob will come somewhere here. And this is going to be L1, let's say. It's going to be L2. This gas will be at pressure P1. This will be at pressure P2. So determine L1, L2 and P1, P2 at the new steady state in the vertical position. So for this, we have to take the barometric value of atmospheric pressure. One atmospheric pressure is equivalent to 75 centimeters of mercury. So this is the question. Okay. Just go through this. We will understand this in more detail. I'll explain how to solve it to you. So initially the tube is in equilibrium in the horizontal situation, in the horizontal state, where on either side of the mercury pellet there is equal amount of hydrogen gas, because you can see the volumes are equal and pressure is equal, obviously, because so there is equal amount of hydrogen gas at 2.5 atmospheric pressure occupying 200 centimeter length of the tube on either side, and the total length of the tube is 450 centimeters. Now from this we take it to the vertical position, so we will see that L1 will become greater than L2 now, because gravity acts downwards on it like that. So in the new vertical position, we have to find out the new values of pressure P1 and P2 and the new values of those lengths L1 and L2. Now, just a small hint I'll give you over here. We have to use the idea that glass is a conducting material. So in the final steady state, the temperature of the hydrogen gas inside the tube in either chamber, the above chamber or the below chamber, will be same as the outside atmospheric temperature, which is 300 Kelvin. And same in the initial state. So there is direct heat conduction between the inner part of the chamber and the outer surface, because glass is a conductor of heat. It's not necessarily a very good conductor of heat, but it's still a conductor of heat. So in steady state, the temperature of gas in either part of the tube will be equal to the outside atmospheric temperature of 300 Kelvin. Okay, so let us see how we will handle this question. Okay, Prachi, we will discuss. Okay, so what is happening is initially you can see that in the horizontal state, we had pressure of 2 atmospheres, volume of 200 centimeters into whatever area, let's say A naught. And this is 50 centimeters of mercury. And same here, P1, V1, and temperature T1 is equal to T naught, where T naught is 300 Kelvin. So this is the initial state of hydrogen in both the chambers. Okay, or 2.5 atmospheres, that's correct. Okay. Now from here, when we go to the vertical state, what will happen is that the weight of this 50 centimeter mercury column will tend to compress this gas and expand this gas. So in fact, let's use a different set of symbols here. So this is at P, V, and same thing. Okay. Now this is at P1, V1, T1. This is at P2, V2, T2. So first of all, T1 will still be equal to T2 equal to T naught, because glass is a conducting material. It is a heat conducting material. So at final steady state, the surrounding temperature will be the same as this. Okay. Now the other thing is, if you look at this mercury pellet, it's experiencing a downward force of pressure into whatever area, an upward force of pressure into whatever area, and it has its own weight, mg. Okay. So P2 minus P1 into this area should be equal to the weight, which is density of mercury into 50 centimeters into that area into G. So the relation that P2 minus P1 should be 50 centimeters into density of mercury into G. So this is an important equation for us. Okay. Now, also, given that the initial pressure was 2.5 atmospheres, and also given to us that 1 atmospheric pressure is equivalent to 75 centimeters of mercury, that means it is this much. Pressure is expressed in barometric value as rho gh, so it's that much. Okay. So that means P is equal to 2.5 into density of mercury into 75 centimeters into G, where this rho is density of mercury. Okay. So hope this equation is clear to all of you. And the other thing is, if L1 is equal to x centimeters, L2 is equal to how much? It is 400 minus x centimeters. So V1 is becoming AL1 or E naught L1 or E naught into X centimeters, V2 is becoming E naught L2. So E naught into 400 minus X centimeters. Uh-huh. 50 सेंटीमीटर्स तो मर्क्यूरी है ना बेटा, ये 50 सेंटीमीटर्स है ना. सो L1 और L2 का सम कितना होना चाहिए? शुड बी 400 सेंटीमीटर्स ओनली ना. Understood now? So now we just use equation of state. So PV upon T should be equal to P1 V1 upon T1 should be equal to P2 V2 upon T2. Okay. So this will give us a relation that so in this of course T is equal to T1 is equal to T2 is equal to T naught. So this equation actually becomes so these two values we can substitute here. Pressure into area, that part. This is coming from free body diagram, beta. Just a second, I'll share that again. Yeah. So Shikhar, this is coming, this equation, this is coming from free body diagram. Force is equal to pressure into area. So if you look at the tube, inside the tube, if this gas is at pressure P2 and this gas is at pressure P1, on the mercury pellet, this will be applying a downward force F1. This will be applying an upward force F2. So F1 will be pressure into that area and F2 will be this pressure into area. So now you can see that this is the free body diagram of the mercury pellet. So it should be in equilibrium. So this. Is it clear now? Okay, good. Now what you will have to do is you have to express P1 and P2 in terms of X in this equation. In this equation which I have tick marked now, you have to express these two. So in these two, P1 and P2 are in terms of the single variable X. So you'll get a single equation in X. I mean, you'll get an equation with a single variable X. So substituting this, we can take 2.5 into 200 into 75 centimeters into density of mercury into G common. So for P2, we have 1 upon 400 minus X minus P1, we have this. This should be equal to, on the other side, 50 centimeters into density of mercury into G. Okay. So we have X minus 400 minus X upon X into 400 minus X is equal to 50 upon 2.5 into 200 into 75. Okay, just check my calculations here. Is this quadratic equation correct? So from this, we'll get the value of X. 1500X, is it? No, but there's the 400X on this side, no, beta. On the right hand side, there's 400X, no? So it will become that, no? 1500 minus 400. Okay, so that's correct. Okay, and then this term is correct, no? 750 into 400 is 75 into 4 into 1000. So 75 into 4 will give us 300. So 300 into 1000 is 3 into 10 raised by 5. Yes, okay. So X will come out to be in centimeters here. So we'll take only the positive route. Okay. Yes, very good. So this is L1 and L2, and of course P1 and P2 will also determine. So when we answer in atmospheres, P1 will be 2.5 into 200 by X in atmospheric pressure. So that will be marginally less than atmospheric pressure. I mean, marginally less than 2.5 atm. Yeah, so it will be about 2.21 atmospheric pressure, and P2 will be marginally more than atmospheric pressure, marginally more than 2.5 atmospheric pressures. So these are our two final answers. So a lot of interesting type of problems can be solved like this by just using the basics of the kinetic theory of gases and kinetic model of an ideal gas, including the equations that we get from it. That we'll do a summary of the equations in the end also, but these are the equations we've seen so far. Okay, so hope this calculation is clear. Yeah, I will scroll up. Just give me a minute. Yes, Shikhar. This is the solution from the starting. So in this, you can see that this is the initial state and this is the final state. Okay, so the final part is just the solving of the how did we get that? Na? See, mass of mercury na, in this equation, this one here, Shikhar, the right hand side of the equation is mg. So mass of mercury will be density of mercury into volume. Okay, so that will be density into 15 centimeters into that area. So that's how we got that. Is it clear now? Okay. And the rest of the solving from here is just the quadratic equation solving. Once you substitute pressures P1 and P2 in terms of X in this equation, P2 minus P1 is equal to 50 centimeters into rho G. Now, the other thing is how we express the barometric pressure. So pressure is expressed as density of mercury into certain length into G, where L is a length of a mercury column of same pressure P. The density of mercury is 13.6 gram per cc. We will be doing a chapter called fluid mechanics in which we will see barometric concept in more detail. It is 13.6 gram per centimeter cube. For example, density of water is 1 gram per cc. So you can see in comparison, mercury is that much heavier. Density of ice is even less than water. It is 0.9 gram per cc. Density of something like wood is about 0.5 or 0.6 gram per cc. Again, you also hope this question is fully clear now. Okay, next up we'll move on to another very important set of relations using the kinetic model of the ideal gas. So next thing is Vrms in terms of absolute temperature, capital T. So now this is not a new derivation, it is just a rearrangement of the earlier equations. So we had seen that RMS speed was square root of 3 PV upon number of molecules into molecular mass, or that is the same thing as 3 PV upon number of moles into molar mass. This was from the kinetic model, okay, using perfectly elastic collisions and all that. And Brownian motion and all that. Okay. Now we had also seen that half mv RMS square was proportional to temperature, and from that we got the relation that PV is equal to nRT, or number of molecules into K into T. So now we substitute this equation in this one. We will get the relation that this is the relationship between temperature and RMS speed, or we can also express this as so this is the all important relation of VRMS and absolute temperature relation. So as I said, there's nothing new over here. We are just manipulating the two equations that we've already got from applying the kinetic model assumptions and collision theory, etc. And of course, kinetic interpretation of temperature. So this equation here, this was coming from and then we verify the ideal gas equation of state that we get. It agrees with experiment because it agrees with Boyle's and Charles' law, which is basically experimental laws also. Okay, now next up from this, we will see that the relation between the average kinetic energy of a gas molecule and temperature, that will further be given by this. So if we substitute this over here, this one, this will become half m this is as per kinetic model of an ideal gas. So in that we are assuming gas molecules are tiny spheres, are point masses. But in reality, gas molecules can take different shapes also. So for a diatomic gas like oxygen, the molecules are shaped like a dumbbell shape. Whereas in kinetic model of ideal gas, we are assuming the gas molecule to be a point mass. So in reality, this is only applicable for monoatomic gases. Helium, argon, etc. But diatomic gas molecules, hydrogen, oxygen, nitrogen, etc., the molecules are dumbbell shaped. And for polyatomic gas molecules, they are more complex shapes. For example, methane. So the gas molecules are tetrahedral in shape. More complex. Sometimes even for polyatomic, it can be very simple. Example, carbon dioxide, more or less this shape only, because this kind of a structure. So it's a linear shape molecules. So we can have a polyatomic gas molecule which is linear in shape also. But generally polyatomic gas molecules are not linear, they are three-dimensional in shape. They become like rigid bodies. So therefore, in general, we should take this as the translational kinetic energy. Instead of the average kinetic energy, we should think of this like the average translational kinetic energy. Because a polyatomic gas molecule, which is more complex in shape, or even a diatomic gas molecule, have rotational motion, not just linear motion or translational motion. So along with the RMS speed of the molecule, which is basically like the center of mass's velocity, it can also have rotation about its center of mass. In case of complex polyatomic molecules, there can also be vibration of the atoms with respect to the center of mass. So this will bring us to a very important principle next over here. So anyway, hope you understood that this. So therefore, in general, that means for monoatomic or diatomic or polyatomic, whatever be the case, half mv RMS square, this is called the average translational kinetic energy. In case of diatomic and polyatomic gas molecules, their motion will be a combination of translation, which is basically given by the center of mass's velocity, and rotation about the center of mass with angular velocity omega. So kinetic energy will be a combination of this kind of quantity, where I is thing called moment of inertia, which you will learn in rotational mechanics very soon if you haven't already. Basically, when a rigid body is moving in such a way that its center of mass is having a linear velocity vcm, but about the center of mass it's also rotating with an angular speed omega, that time the kinetic energy is given as kinetic energy of translation plus kinetic energy of rotation. This is called something called rigid body motion. It's a combination of rotation and translation. For example, if you just imagine I have thrown this pen like this, so it's going in a motion like this. It's in a combination of rotation and translation. The center of mass is in motion, but about the center of mass it's also rotating. Yeah, in the case of complex polyatomic molecules, there can also be vibration about the center of mass. Even in diatomic molecules, Prajit is correct, it can happen, but generally it happens at extremely high temperatures. So for diatomic molecules, we assume that the kinetic energy is only the sum of translation and rotation. Whereas for complex polyatomic molecules like methane or uh, ammonia or those kind of three-dimensional molecules, there can also be vibration. So the total kinetic energy becomes the sum of translational plus rotational plus vibrational kinetic energy. Yes, yes, Smith, that is correct. Rolling is an example of combination of rotation and translation. When a cylinder is rolling down an inclined plane, or like a sphere is rolling on a floor or on a horizontal surface, like the snooker or billiards balls rolling on billiards table. Okay, so you can just make a note of this point. So keeping this in mind, so therefore, from kinetic theory of gases, we have half m v RMS square is 3 by 2 kT. So this is basically the average translational kinetic energy per molecule. This thing is 3 by 2 kT. Okay, so that brings us to a conclusion of today's lecture. Now, next time we will discuss something very important related to this called the law of equipartition of energy. And the concept of degrees of freedom. And from that, we will get into first law of thermodynamics, which is the most important section of this heat and thermodynamics. This is the most important part. Okay. We will also see something called Maxwell's distribution curve. Something called most probable speed of a gas molecule instead of RMS. and also mean speed instead of RMS. Okay. So I will send you a list of questions that you can do from H.C. Verma's Kinetic Theory of Gases chapter. And of course, you can do questions from the module. We'll keep aside some question for some time for doubts also. So in the next lecture, we will discuss some questions which you might have done from H.C. Verma and the module for this thing, thermal expansion as well as calorimetry. And then we will move on with these additional sections. Okay. So you can read ahead about equipartition of energy and degrees of freedom. Okay. That will help for the next lecture's theory part, and also complete maximum problems of calorimetry and this thing, thermal expansion. And if there are any doubts, keep them ready. We'll discuss in the next lecture. So that's it for today's session, people. Wish you all the best.